Glass casting allows us to fully explore the shaping potential of the material. By pouring molten glass into a mold, we can create three-dimensional glass components of virtually any cross-section and shape, as showcased in various glass art objects. In architecture, only recently have we started to explore the potential of cast glass as a three-dimensional expression of the material that can take full advantage of its high compressive strength. According to the starting state of glass casting can be divided into primary and secondary casting. In primary casting, glass is founded as a hot liquid from its raw ingredients. The main process of primary casting is hot pouring or melt quenching. In secondary casting, glass already made in solid pieces is reheated until it can flow and be shaped as desired. Thus, the secondary process requires lower operating temperatures compared to those for founding glass. The main process of secondary casting is kiln casting. The principal difference between the two methods, besides the initial state of glass, is the required infrastructure. Kiln casting employs a single kiln for the melting of already formed glass into molds and for the subsequent annealing process. In contrast, in hot pouring, molten glass from a furnace is poured into a mold and is then placed in another second furnace for annealing. In both methods, the annealing process is similar. Initial glass is heated until it is molten enough to flow into the mold. Once the mold is filled, the glass is rapidly cooled to a few degrees below its softening point. This rapid cooling stage, called quenching, is essential for preventing a crystal molecular arrangement of the melt. During this phase, the glass's relatively low viscosity allows any induced thermal stress to relax to a negligible amount immediately. When the glass temperature drops below its softening point, the viscosity of glass is sufficient for it to retain its shape and not deform under its own weight. At this point, the annealing process of the object starts, aiming at eliminating any possible differential strain and preventing the generation of internal residual stresses during further cooling. The cast glass should be maintained for adequate time at the annealing point to release any existing strains and then cooled at a sufficiently slow rate to prevent the generation of residual stresses when the glass temperature has reached equilibrium. Effectively, below the strain point, stress is unable to relax in time and is considered permanent. When the temperature of the entire object has dropped below the strain point, it can cool at a faster pace until ambient temperature, yet adequately slow to avoid breakage due to thermal shock. During annealing, the magnitude of the resulting internal stresses is largely determined by the temperature difference between the warmest and coolest parts of the glass. This in turn is influenced by various factors such as the glass's thermal expansion coefficient, the glass element's thickness and mass distribution, its size exposed to cooling, the amount of other thermal mass in the furnace, even the geometry and characteristics of the furnace itself. In practice, as it is rather challenging to estimate the exact heat transfer occurring within the annealing oven, the annealing schedule of large three-dimensional cast elements is often based on practical experience. As a general rule, round or ellipsoid shapes and equal mass distribution are key aspects for the prevention of residual stresses.
The choice of mold depends largely on the casting method, the production volume, and the desired level of accuracy of the glass product. They can be disposable or permanent. Disposable molds are more efficient for single component or small batch castings. The attained level of achieved accuracy and maximum melting temperature can vary. From cheap investment silica plaster molds for castings below 1000 Celsius degrees to 3D printed sand molds and milled alumina silica fiber ceramics of top performance. In all cases though, the glass surface in contact with the mold will acquire a translucent, rough skin that requires post-processing for a transparent result. Due to the brittle nature of these molds, quenching is not recommended, thus their common application is in kiln casting. For a series production, permanent molds from steel or graphite are preferred in combination with a melt quenching technique that is more time efficient compared to kiln casting. Such molds offer considerably higher dimensional accuracy. The coating of the steel mold with a release agent, usually boron nitride or graphite, is crucial for the easy release of the glass component. Permanent molds can be open-faced, can be adjustable to allow for safe flexibility, or pressed to offer a higher dimensional accuracy. Overall, the resulting surface is glossy and transparent, requiring minimum to no post-processing. Finally, although the complexity of the shape is not a significant cost-affecting factor for disposable molds, it can sensibly increase the price of steel and graphite molds. Solid cast glass components are a promising solution for engineering pure glass structures of high transparency that take full advantage of glass's compressive strength. Nonetheless, so far, there are limited applications of cast glass in architecture, and almost in all of them, the cast glass components are confined to the size and shape of a standard brick. The reason behind this is the prolonged annealing time required to cool down massive cast glass components. The giant ground-based telescope mirrors, which are the largest monolithic cast glass pieces ever made, are the perfect example to explain this. These multi-ton glass pieces span several meters and require several months or even years to be properly annealed. Thus, in respect to the lengthy cooling time, in architectural applications, solid cast glass components have been commercialized up to the size range of standard masonry bricks. Repetitive shapes are typically employed as they result in the fabrication of a few high-precision metal molds. Typical glass compositions used are either soda lime or borosilicate. Characteristic such examples are the Crystal House's facade in the Netherlands, the Kamat Pavilion in Greenland, the Optical House in Japan, the Ice Falls in New York, while a project that stands out in terms of glass component size is the Mirage sculpture in Apple's headquarters in California, where each column is 2 meters high and 15 centimeters in diameter. But there are ways to achieve bigger monolithic glass components of reduced annealing time. Going back to the telescope mirrors, by optimizing their mass to stiffness ratio and choosing a glass recipe with low thermal expansion, bigger telescope cast glass discs are possible with a significantly reduced annealing time, still of a few months. The same principle of topology optimization can be used to create monolithic architectural glass components of substantial dimensions, yet with a feasible annealing time of just a few days to weeks. Perhaps we are not far from seeing such massive cast glass structures being realized.